Hello everyone, welcome in the video lecture of Integrated Circuits. I am Goel, Assistant Professor in the Department of AKGEC Engineering College. In today's lecture, we are going to discuss about the linear application of operational amplifier, one of the linear application of operational amplifier, that is voltage to current and current to voltage converter. So let us start with the introduction of the topic. Voltage to current converter with the help of operational amplifier. With the help of operational amplifier, we can realize so many applications. Though op-amp is a linear IC, but we can realize linear applications as well as non-linear application with the help of operational amplifier. One of the linear application of op-amp is V2I converter. With the help of op-amp, what we can do, what this circuit can do, it can convert the applied input voltage into its equivalent amount of current. So, V2I converter is a kind of circuit where we can convert the input voltage into the output current. A V2I converter we can realize with the help of op-amp in two ways: floating load V2I converter and grounded load V2I converter. One by one we will discuss both of them, floating load and grounded load. After this, we will discuss the reverse of V2I converter, that is current to voltage converter. So, let us start with the introduction of floating load V2I converter. What is floating load V2I converter? Let us first understand the meaning of floating load. When we want to convert voltage into current with the help of op-amp, we are required to connect a load in our circuit. If the load we are connecting in the circuit is not connected directly to the ground, then it is called as floating load. What is the meaning of floating load? Here we have one circuit diagram for our reference. What is the meaning of floating load? We are connecting our load at this point, which is the feedback path of the operational amplifier, and either of its terminal is not directly linked with the ground. So, it is called this configuration of V2I converter where load is not directly connected with the ground is called as floating load V2I converter. Okay. So, this is the circuit diagram of floating load V2I converter. We can realize this floating load V2I converter in many ways. This is one of them. Here what we have done, we have connected our input signal or the input voltage that we want to convert into the current at the non-inverting terminal of operational amplifier. The load we have connected in the feedback path, the feedback is negative and where we have one constant input resistance. The current, now what we want to show, how we will show that this circuit is working as V2I converter. To prove that this circuit is converting as V2I converter, we are required to show that the current flowing across the load is directly proportional to the voltage. Generally what happens, if we will change the value of resistance, then the amount of current flowing through it will also get changed. For example, if we have a resistance of 1 kilo ohm, the current flowing across this resistance corresponding to some voltage will be some value. If I will change this value of resistance from 1 kilo ohm to 2 kilo ohm corresponding to the same input voltage, then the amount of current flowing through it will get changed. So, the value of current flowing through a resistor will depend upon the value of resistance. But here what we are saying, in V2I converter, the current flowing across the load is independent of the load value and it is proportional to the applied input voltage. So, if we can show this relationship or if we can prove that the load current is proportional to Vi rather than the load resistance, we can say that this circuit is working as V2I converter. Okay. So, here our aim is to show that this load current is proportional to Vi. So, let us solve the circuit. Here we have the same circuit diagram where the input voltage we have applied on the non-inverting terminal. Here at the inverting terminal, with the help of negative feedback path, we have connected a load resistance through which our load current is flowing, that we want to show is proportional to the input voltage. Here we have one input resistance connected to the ground at pin number 2 or the inverting terminal of op-amp. So, with the help of, first let us do the mathematical calculation. First, with the concept of virtual short circuit, we know that the voltage at non-inverting terminal and at inverting terminal is same. What virtual short circuit concept says, the voltage at both the terminal is used to be same. So, if the voltage at the non-inverting terminal is V in, then the voltage at this particular point will also become V in. Let us consider the current across this load is IL and the current across this resistance is I in. As we know that the current entering inside the op-amp is always 0. Why the current entering inside the op-amp is 0? Because of very high input impedance of op-amp. This is one of the ideal property of op-amp, that its input impedance is infinite. Practically it is very high in mega ohm. So, the current entering inside the op-amp we always consider approximately 0. So, with the help of this concept, if no current is entering inside the op-amp, the current here is IL, the current here is I in, we can write IL is equals to I in. What we can say, that the load current is equals to the input current. The input current we can calculate like it is flowing between V in and ground. So, I can replace this input current with V in minus 0 divided by R. Okay. So, from this what I can say, for a constant value of resistance, here we have the input resistance. If the value of this resistance is fixed, I can say that this IL is proportional to the input voltage. That we want to show, or that we want to prove, that IL is independent of this load resistance and it is depending upon the input voltage. So, here what we have done, we have converted the input voltage into its equivalent amount of current. Okay. So, this is floating load V2I converter. Floating load V2I converter is also known as transconductance amplifier. Transconductance amplifier, because here what we are getting, we are applying voltage at the input and we are obtaining current at the output. Okay. So, output current upon input voltage is transconductance amplifier, and we can also call this circuit as voltage controlled current source. We are applying voltage at the input and we are getting current at the output. So, what we can say this circuit, how we can name this circuit? We can name this circuit as V2I converter, floating load V2I converter, transconductance amplifier, or voltage controlled current source amplifier. So, this is about floating load V2I converter, where the load is not connected to the ground terminal. The next configuration of V2I converter is grounded load V2I converter. What is grounded load V2I converter? As the name indicates, any one terminal of the load must be directly connected to the ground. If in the circuit where the load is connected, any one terminal of that load is directly linked to the ground, then that configuration of V2I converter is called as grounded load V2I converter. This is the meaning of this term, grounded load V2I converter. So, here we have this circuit configuration for our grounded load V2I converter. Our aim will remain same, that we want to show that the load current is proportional to the input voltage and it is independent of the load resistance. Okay. So, this is V2I converter and this is grounded load V2I converter, because the load is connected directly to the ground terminal. Fine. So, in this circuit again we want to show that this IL is proportional to V in and is independent of this load resistance. How we will show? We have to do some mathematical calculations. Here, how we have connected or how we have realized this grounded load V2I converter, we have connected the load resistance to the non-inverting terminal of op-amp. The input voltage is also applied at the non-inverting terminal of op-amp. At the inverting terminal, two resistors are connected. Let us consider that all these four resistors are of same value. Now, our aim is to show that this IL is proportional to V in. So, let us start the mathematical calculation, how we can show this thing. First, let us observe this op-amp circuitry. In this op-amp, if we will observe whether it is inverting configuration or non-inverting configuration, it is in non-inverting configuration. Non-inverting configuration means the input signal is applied at the non-inverting terminal of op-amp. If we will apply this input signal at the inverting terminal of op-amp, then the op-amp will become in inverting configuration. Okay. So, our op-amp is in non-inverting configuration. Let us consider the voltage at this T point is V1. Okay. Now, we know for non-inverting configuration of op-amp, what is the relation between the output voltage and the input voltage? Here, we have applied the input signal at this point, but it is not directly appearing to the non-inverting terminal of op-amp. So, we know the relationship between the output voltage and the input voltage of non-inverting configuration of op-amp is V out is equals to V in 1 plus RF divided by R in, where RF is the feedback resistance and R in is the input resistance. V in is that voltage which is directly appearing at the non-inverting terminal. V in this case may be V in or it can be any other value also, but that V in is that value of input voltage which is directly appearing at the non-inverting terminal. In our circuit, V in is not directly appearing at the non-inverting terminal of our op-amp, while we have considered that V1 is the voltage which is appearing at the non-inverting terminal. So, we will replace V in with V1. So, what it will become? V naught is equals to V1. 1 plus feedback resistance upon input resistance. What is the value of feedback resistance is R. What is the value of input resistance is? Again the R. So, we will replace RF by Rn with R by R. It will give you the value of 2 times of V1. Okay. So, this is our first relationship. Let us say the output voltage, this output voltage is equals to twice of V1. Now, let us move forward. What we want to show? We want to show IL is proportional to V in. So, again if we look our circuit, here we have V in. Let us consider one current I1 is flowing across this resistance R. At this point, this current will divide in 3 paths. One going towards the RL, another current is going towards this particular resistance R, the another current entering inside the op-amp. Let us say it is Ix. Okay. So, how I can divide this current I1? I1 in this case will become the summation of Ix plus IL plus I2. Okay. Now, we know that the current entering inside the op-amp is always 0. Why 0? Because of very high input impedance of operational amplifier. So, we can write Ix is equals to 0. Now, I1 is equals to IL plus I2 only, or what I can write that this IL is equals to I1 minus I2. I can write here I have rearranged the equation. IL is equals to I1, I2 is I2 will become minus. It will put this I2 at this point. It will give us IL is equals to I1 minus I2. Now, we will mention the value of I1 and I2 in terms of voltage and resistances. So, we will write IL as it is. What is the value of I1? I1 is the current flowing in this particular branch. So it is flowing between V in and V1. So what will be the value of I1? V in minus V1 upon R. So instead of I1, I can write V in minus V1 upon R minus of I2. I2 is the current is flowing between V1 and V naught through this resistor R. So I can replace I2 as V1 minus V out divided by R. Got it? From equation 1, we have relationship between the output voltage and V1. That is, V out is equals to twice of V1. So here I will replace V naught with twice of V1. So in this case, what our equation will become? Our equation will become IL is equals to V in by R, let's say, minus V1 by R minus V1 by R, minus minus will become plus twice of V1 by R. Got it? So now if I'll observe this equation, further if I'll solve this equation, what I'll get? IL is equals to V in by R minus V1 by R minus V1 by R will become minus of twice of V1 by R. Here we have plus of twice of V1 by R. So these two terms will be cancelled out with the last term. So we will left with IL is equals to V in by R. So our load current is equals to V in upon R. For a constant value of this resistance R, what I can say that IL is proportional to the input voltage. This is what that we want to prove. We want to prove that the load current is independent of this load resistance and it is depending upon the input voltage. IL is proportional to the input voltage. That means the voltage that we are applying at the input will convert into its equivalent amount of current across this load resistance, and this configuration is grounded load V2I converter. Got it? Though we are saying that this load current is independent of load resistance, what is the meaning of this line? That the load current is independent of load resistance means if I'll change the value of this RL, IL should not get changed. Okay, but this relationship of IL and RL will be followed up to a particular value of RL. It is not like we will keep on changing the value of RL. We can keep any value of RL and IL will not get affected by RL. It is for lower values of RL. Within a particular range, it will change the value of RL, IL will be proportional to V in. Got it? So this is how we can convert voltage into its equivalent amount of current. Next, where we can use this application of V2I converter that we have realized with the help of op-amp, we can use this application of V2I converter for testing diodes, LEDs, Zener diodes, for testing Zener diodes, LEDs, normal P-N junction diode, and in low AC and DC voltmeter. How we can use this particular V2I converter to test the diodes or LEDs? It will replace this load resistance with any of the diode or any of the LED. Then if that diode or LED is working properly, we will get the value of load current changing according to the input voltage and the LED will glow. The another application of this V2I converter is to find the match of diodes. Match of diodes means if I have multiple diodes and I want to find out the identical diodes, then I will replace this load resistance with diodes, and if I will get the same load current across two diodes corresponding to the same input voltage, then we can say that those two diodes are identical. Further, this V2I converter can be used in low voltage AC and DC voltmeters. Okay, so this is all about V2I converter, where we have seen that it can be realized in two ways: floating load V2I converter and grounded load V2I converter. The next is I to V converter. In V to I converter, we have seen that how we can convert the input voltage into its equivalent amount of current, and where we can utilize this V to I conversion. Here in I to V converter, we have to perform just opposite of V to I converter. In I to V converter, at the input we will apply the current, and at the output we will measure the voltage, and that output voltage should be proportional to the input current. If we are able to fulfill this relationship between the output voltage and the input current, then that circuit will be called as I to V converter. So here we have one way with the help of which we can realize this I to V conversion, with the help of which we can convert the input current in the output voltage. How we have realized this I to V converter circuit with the help of op-amp? Here op-amp is connected in inverting configuration. Why inverting configuration? Because this time the input signal is connected to the inverting terminal of the operational amplifier. The non-inverting terminal of op-amp is grounded. At the input, this time we have connected a current, because this is our I to V converter, so we have to apply a current at the input. So at the inverting terminal, we have applied a current source as an input signal. Further, in the feedback path, we have connected our load resistance RF, across which we will calculate our output voltage. Fine. So if we are capable of showing this relationship that this output voltage is proportional to I in, we can say that the circuit is behaving like I to V converter. So how we can solve or how we can show this relationship? We know again with the help of virtual short circuit. If the potential at the non-inverting terminal is ground, the same voltage will appear at the inverting terminal of the operational amplifier. This is called virtual ground of virtual short circuit. Fine. So at the non-inverting terminal, we are having 0 volt, it is grounded. So at this point, the voltage will also become 0 volt. Now this current I in is flowing. At this point, this current will divide in two parts. One current will go in the feedback resistance, another current will go inside the op-amp. But we know the current entering inside the op-amp is always 0 because of high input resistance. So what we can say, that this I in is equal to the feedback current. Fine. So what I can write, this I in is equals to what value? Now this I in is flowing between this 0 volt and the output voltage. So what I can write, I in is equals to 0 minus V out divided by RF, or this I in will becomes equals to minus of V out upon RF. Again, for a fixed value of this feedback resistance, what I can write, I can mention that this input current is directly proportional to the output voltage. This input current is directly proportional to the output voltage, or this output voltage is directly proportional to the applied input current value. What this negative sign is indicating here, this negative sign is indicating that we are using inverting configuration. Okay, so it will take the output voltage is directly proportional to the input current, or what we can say, that this circuit is behaving like I to V converter. What is the another name of this I to V converter circuit? We have seen in the V to I converter, the voltage was input, the output was current. So the ratio of current to the input is transconductance amplifier. Here input is in current, output is in voltage. So output voltage upon input current is called trans-resistance amplifier. This can also be called as trans-resistance amplifier, where we are having voltage as an output and current input. Or what another name we can give to this circuit? Here we have voltage as an output. So we can say, or we can call this circuit as source. So the third name of the circuit can be current. Okay. So this I to V converter, what is the function of this I to V converter? Is to convert the input current into its equivalent amount of output voltage. We can call the circuit as transresistance amplifier, or we can call the circuit as current controlled voltage source. So let us check where we can use this I to V converter. The main application of this I to V converter is to sense the current from the photodiodes, photodetectors or photovoltaic cells, and to convert that current into its equivalent amount of voltage. How we can realize or how we can utilize this I to V converter for sensing current from through photodiodes or photocells? Here in this circuit diagram, we have utilized our I to V converter for sensing current from the photodiodes. Here one photodiode is connected at the input side. How this photodiode will operate? We know how photodiode works. Photodiode is a kind of diode which is used in reverse biasing. When light falls on this photodiode, then the intensity of light will be converted into equivalent amount of current, but the value of that current is very small. We can convert that current into useful amount of voltage with the help of further I to V converter circuit. So here we have connected one photodiode at the input of I to V converter. When light will fall on this photodiode, that will be converted into input current. The light falling on this diode will be converted into the current. That current will work as an input current for our I to V converter. Further, this current will be converted into the equivalent amount of output voltage. So with the help of this I to V converter, actually it is very important application of I to V converter. So with the help of this I to V converter, we can sense current through the photodetectors, photocells, photodiodes and photovoltaic cells, and can convert that current into its equivalent amount of voltage, or even further we can amplify that voltage into useful amount. Okay. So in this V2I and I to V converter, we have seen how we can convert voltage into current and current into voltage. These are the linear applications of op-amp, operational amplifier. Further, we can use V2I converter for finding the match of the diodes, for testing LEDs and diodes, for AC and DC voltmeters, for low voltage AC and DC voltmeters, and we can use this I to V converter for converting current, for sensing current and then converting current into the useful amount of voltage. This is all about V2I and I to V converter. Thank you everyone.